Okay, so in this next lesson, we're going to go ahead and talk about solving exponential equations, which are, by their name, they're equations that just involve exponents, and we're going to get into using logarithms to solve them in this case. There are two types of problems we're going to start with. The first one is a problem of the following type. Okay, so in this problem we have 3 to the x equals 9 to the x plus 5. And so if you look here, there are two different bases for the exponents. So you have a 3 here as a base here, and you have a 9 as a base here. And in this problem, we're going to use the following fact. So this is just something that you can kind of remember. So if you have two exponents, and on one side you have some number b to the x, and on the other side of an equation you have some number b to the y, well, that means that x has to equal y. So if you look here, it kind of intuitively makes sense that if the bases are the same for the expressions, then the exponents also have to be the same. In other words, they have to be equal. So if we look at the problem over here, the problem is right now that I can't use this fact because I have a 3 and a 9, which are different bases. But what you can do is you can kind of think about, well, I do know that 3 squared is 9, so what if I were to rewrite the equation as follows? Right, so you should agree that 3 squared is equal to 9, so that you now have the same base, and now you can actually just kind of walk along here and use your exponent properties, right, and apply this 2 to each piece of that exponent there, so that you now have 3 to the x equals 3 to the 2x plus 10. So in other words, I kind of distribute that exponent to each of the two pieces here and here, so the 2 goes to the x and the 5. And now I have this nice setup where I have two of the same bases. These are kind of like my b's here, and so I can take each exponent and set them equal to each other, and you'll see that you have a simple linear equation that you can solve. Okay, so then you just go ahead and finish this problem out, combining like terms across the equal sign, and then we want the positive version of x, so we get x equals negative 10. And you know, you can always go back to the beginning and you can plug in x here and make sure that indeed the left side is equal to the right side, and that in this case you would get that. I'll let you do that on your own, but you can always go back and check your work too. Okay, but this raises an interesting question of what if I can't rewrite these two bases so that they're equal to each other? So that is where logarithms are going to come in. So let's look at a second type of problem. So we'll call this problem number 2. And we're going to start out with a fairly simple one. Okay, so if you look here, we say 4 to the x is equal to 38. So I'm saying, what power do I have to raise 4 to get to 38? And if you kind of think about that for a few seconds, you'll realize that there's no integer or nice number, more informally, that I can raise 4 to get to 38. Okay, so to get the exact answer, what I'm going to do is, again, I have this issue of I can't write 38 as a base of 4. There's no power 4 can be raised to get to 38. But what I can do is I can use logarithms, which is the tactic that we're going to use in this case. So what I'm going to do is I'm actually going to take the logarithm of both sides, and I'm going to specifically use the log base 4. Okay, and I'll show you in a second why. Okay, so if you look here, I've taken log base 4 of the left side and log base 4 of the right side. So that's literally all I've done. I've done it to both sides because it's an equation. I want to keep it balanced. And then if you use your properties, we know that there is a property that says I can bring this x out front because it's an exponent, right? We talk about that exponent property for logarithms. So on the next line, what I'm going to do is I'm going to write it as x log base 4 of 4 is equal to log base 4 of 38. The other side I haven't done anything with yet. And then if you look here, log base 4 of 4, this works out very nicely because log base 4 of 4 is 1, because 4 to the first power is 4. So in other words, you can kind of think about these as canceling out and you're just left with x is equal to log base 4 of 38, okay? Now, as you get quicker with this, you won't necessarily have to draw this arrow showing that x is down here. You can just say, okay, log base 4 of 4 raised to the x automatically jumps to this piece here, x equals whatever the other side is. And now we're actually going to use what's called the change of base formula, because I don't have a log base 4 in my calculator. I only have log base 10 and log base e, or in other words, ln, the natural logarithm. So what I can use is the change of base formula, and I can say, okay, well, x is going to be equal to ln of 38 over ln of 4, okay? Or if you like to, you can say log base 10 of 38 divided by log base 10 of 4. And actually, you can use any base here that you'd like, as long as you use the same base in the top and the bottom. And the way I always remember that is the base here stays in the basement, so it goes below, and this bigger number here stays up top, okay? And if we actually do this in our calculator and we round it to, we'll round it to the nearest thousandth, you'll get 2.624, okay? So in the end, I found that 4 raised to 2.624 roughly is equal to 38. Okay, so that is kind of our second type of problem with exponents. Let's do a few more practice problems with that second type. So we'll call this problem 3. And this one I'm going to say 12 to the, let's make it x plus 3 plus 8 is equal to 35. Okay, so here I'm going to kind of use the similar tactic as in this problem here, where I'm trying to get this x out of the exponent so that I can actually solve for my answer, okay? So if I go back to this problem, first thing I need to do, though, is I need to move this 8, just like you would any other equation. So I'm going to go ahead and subtract 8. Okay, so that I'm left with 27 on this side. And now, just exactly how we did on the other problem, I'm going to look at this base here of this exponent, and because this is the base that has the x here, I'm going to use log base 12 of both sides to eventually get rid of the 12 here and bring the x down. So I'm going to say log base 12 of 12 to the x plus 3. And then what I do to one side, I also have to do the other. So I'm going to do the log base 12 of the right side as well. Okay, and you can kind of think ahead that you're going to have to use the change of base formula here. So again, if I think in terms of cancellation, log base 12 of 12 is 1, so these kind of go away, and I'm just left with the x plus 3 is equal to log base 12 of 27. Okay, and in this case, we just have this extra 3 here that I need to subtract. So we'll say x is equal, or approximately equal to log base 12 of 27 minus 3. I like to use the natural logarithm for the change of base formula. You don't have to, though. Okay. So in my calculator, I'm going to go ahead and do ln of 27, or whatever base you choose, divided by ln of 12. Just make sure they're the same base. All minus 3. And when you do that, your final answer comes out to negative 1.674, approximately, rounding to the nearest thousandth. Okay, and again, you can always go back if you have extra time, use this approximation, see if you get about 35, since we had to round here. But in this case, you'll be able to see that it does work. Okay, so let's do one more problem. So we'll call this one number 4. And this one we're going to use Euler's number E. We'll say this is equal to 41, okay? Same idea. So I'm going to go ahead and add 5 first. Okay. And now, and actually let me leave myself a little room here. And now, because I have E, Euler's number, well, what logarithm of a base would I have to use to get rid of E? Well, the log base E. So I'm going to say log base E, which we denote as ln, I'm going to do it to both sides. So again, whatever this base is here, attached with the x and the exponent, I need to get this x down eventually, so I'm going to use this as the base that I choose down here. Okay, it's just that for ln, I know that that means log base e. Okay, maybe we'll make a note of that. So if you're taking ln of some number, that's the same thing as log base e of that number. Okay. So now if I look here, I can see that ln of e is going to be equal to 1, so these get canceled, and the 3x comes down because of that property we talked about on the first problem, or the second problem. And so now I have this here, and I'm just going to go ahead and divide by 3. Okay, same goal as any other equation. Get x by itself. Okay, and ln of 46 divided by 3 is approximately 1.276. Okay, so there you have another problem, in this case using the Euler's number with a natural logarithm, all using the same tactic of getting rid of those exponent bases to get the x, or the variable that you're solving for, out of the exponent and solve whatever remaining equation is left. Okay, so in our next video, we'll go ahead and talk about how to solve logarithmic equations using exponents and the relationship between the two. Thanks for watching.